Hi scholars, today we're going to go over one problem in which we calculate the average rate of change over successively smaller and smaller intervals. So just to recap real quick, when we talked about average rate of change, right, in your mind you really want to think about slope. And it's a way of sort of calculating the slope of nonlinear functions. Now, of course, nonlinear functions like y equals x squared doesn't have one slope, right? Only lines have a slope. But what we can do is we can say, for example, here's a point. Let's call that point A, right? And here's another point B, right? We can call that point B. And at A, this function has a value of f of A. And at B, point B, right, this function has a value of f of b, and we could say that if we wanted to approximate the slope, right, that between these 2 points A and B, we could do it by just calculating the change in y, right, we'll do the same color, the change in y over the change in x, right, in this case. Now it's not a line, but we can approximate it. We can say it's as if it was a line between points A and B, and so we can use our slope formula, which is now our average rate of change formula, and say that the average rate of change between this point right here and this point right here is nothing more than f of b minus f of a over b minus a, and it's nothing more than that, which is nothing more than change in y over change in x. Okay, so let's take a look at an example. Approximate the slope of f of x equals x cubed, this is the graph, at x equals 2. So this right here is already something that's new, right? When we talk about slopes, what we need is 2 points, right? You always say to find the slope, you want to find out a change in y. What happens to y as x changes? And if we're talking about a change, we need 2 points. We need to say what's the before and what's the after point, right? So here we want to say we want to approximate. So we're never going to be able to find the slope at a point, but we want to say, can we get closer and closer? So first off, let's start by locating our point at x equals 2 right here, right? There it is. There's our graph, our function. And another way of asking this question of approximating the slope of this function at x equals 2 is to say approximate the slope of the tangent line to this function. So in other words, there's one line out there that passes through, right, at this point in the function, passes through this function at only this one point, right? There is only one line that does that, and we want to say, what's the slope of this line? So how could we calculate the slope? Okay, so we can actually do this by successively approximating and calculating the average rate of change. So let's move this over here, and let's do some calculations, getting closer and closer. So again, we need an interval. So for example, let's say that we want as a first estimate to do the average rate of change between the point when x equals 2 and the point when x equals 3, right? We can see what that would look like. It would look like something like this, and it's not perfect, right? This slope clearly is, the blue slope is not the same as the red slope, but it's a starting place, right? So first off, as a first step, let's try to do the average rate of change between point 2 and point 3, okay? So this would be, again, f of 3 minus f of 2 over 3 minus 2, which is 3 cubed is 27, minus 2 cubed, which is 8, all that over 1. So 27 minus 8 should be 19 over 1. So the average rate of change there is 19. And you say, that's a big number. Well, also notice that just to make it a little easier to see that these x and y axes are scaled a little bit differently, right? So a slope of 19 is actually okay in this particular situation. It's reasonable anyway, okay? So that's a good approximation. So this is our first approximation, right? We're doing approximating. How could I get a better approximation, right, from this blue line, right? So this is number 1. That's our first approximation. Well, if instead of going between points 2 and 3, what about if I tried to go between point 2 and, say, 2.5, right? it looks like that line, the slope of that line, it's a little bit of a better approximation, right? It's a little hard to see, but it looks like here it's a little bit of a better approximation. So let's try it, right? What would it be, the average rate of change between point 2 and the point 2.5, right? We're getting a little closer to just the slope of the line at the point 2, right? So it's another approximation. So we could do f of 2.5 minus f of 2 over 2.5 minus 2. And in order to calculate f of 2.5, we're definitely going to need a calculator. So that would be 2.5, that quantity cubed, right? Equals 15.625. And we're going to say f of 2.5, we said minus f of 2, which is just 8, right? We already did that calculation, so let's do that minus 8. Okay, that's 7.625, so let's record that. So this is 7.625. All of this is divided by 2.5 minus 2, which is 0.5. So we're dividing this all by 1/2. So we can do that, divided by 0.5, same thing as multiplying it by 2. And we get a number 15.25. Okay, so this looks like 15.25, which is different from 19, right? It's closer to what we want, right? We want a slope that's a little less than 19, right? So it's closer to the slope at x equals 2, but it's not quite there yet, right? Can we get a better approximation? Well, sure we can, right? We can get a better approximation if we take this point, this other point that we're using with 2 to calculate the average rate of change, and we make it closer and closer to 2. So let's actually calculate the average rate of change between the point 2 and a point really close to 2, like 2.1, right? That's pretty close. We're getting pretty close here. So let me write that a little nicer. Average rate of change between 2 and 2.1. And let's calculate that. So again, that'll of course be f of 2.1 minus f of 2. You see, we're getting closer and closer to 2 over 2.1 minus 2. Okay, so f of 2.1, again, we're going to need our calculator here. So let's do 2.1, that quantity, all of it cubed. What do we get? 9.261. Again, we're going to subtract f of 2, which is just 8. So let's subtract 8. So 1.261 is what I have. So this is 1.261, and we're going to divide it now by 0.1. Now you could do your calculator. You don't really need to, because you're just dividing by a tenth is the same thing as multiplying by 10. So now I get a number 12.61. Now that looks a little closer, huh? Looks like a little better approximation. Now in our graph, we can't really draw it. It would be really hard, right? But now this line is sort of even in between, right? It's saying now my point is 2 and 2.1, right? It's really hard to even see this, but that's a much better approximation of the slope of f of x, right? And so the question is, it looks like we're going from 19 to 15 to 12, right? Maybe this thing just gets lower and lower, and if I did it closer approximations, right, I'd get to 0 or something like that. So it turns out, no, that's not what happens. It actually approaches a fixed value. It approaches what we call a limit, okay? And for just to see what that could look like, just quickly, let's do the average rate of change, and I won't do it formally, but let's do the average rate of change between the point 2 and 2.001. Oh my goodness, those 2 points, they're so close to each other, you can't even see the difference. It's almost as if they're 1 point, right? They're not 1 point, but we're approximating. We're getting these 2 points really close and saying, what's the slope at that really tiny interval? Okay, so let's do it real quick. So we have 2.001 quantity cubed. Wow, look at that number. That's pretty close to 8, right? And we're doing that subtracted by 2 cubed, right? This is our change in y, our f of b minus f of a. So now I have this number 0.012006, blah, 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 okay? And I'm dividing that by, so again, this is just calculating f of 2.001 minus f of 2 over 2.001 minus 2. What is 2.001 minus 2? It's 0.001. So let's divide it by 0, 0, 1, and see what answer we get. We get 12.006. So this equals 12.006. It kind of looks like all these slopes, as we do better and better approximations, are approaching 12. And in fact, the slope of the tangent line of f of x equals x cubed at the point x equals 2 is indeed 12. Now we'll learn later on that by approximating the slope, we're really approximating the derivative. We're trying to calculate the derivative, and there are nice patterns and shortcuts where we could do this entire question, right, in about 10 seconds, just by using some algebraic manipulation. However, that trick of using the algebraic manipulation is called the power rule. That's a trick that is built upon people throughout history who spent their time approximating, trying to get closer and closer and closer, and doing this sort of in-depth calculations, even without computers, right? Without calculators or anything. People actually spent time doing this hundreds of years ago. So this is actually kind of cool that we can now talk about the slope. So this right here is the slope of the tangent line, right, at x equals 2, and later on we'll say this is the derivative of this function at x equals 2. Have a great week. Awesome.